Okay, folks, so today I'll be telling you about some work we've done involving imaging the freezing and melting of electrons in 2D Wigner crystals. And so what I'll do first is I'll show you my collaborators and funding agencies. So a lot of people contributed significantly to this work from a lot of different institutions. It's too many names to read, so I won't read them, but I did circle one in red, and that's Feng Wang. He was supposed to introduce me. He didn't show up. But the reason I circle his name in red is because my group and his group have worked very closely over the last 5 or 6 years on this topic. And so the results I'm about to show you are just as much from his group as they are from my group. Here's an outline of what I'll be talking about. First, I'll say some introductory words about Wigner crystallization. Then I'll show you some data where we've imaged generalized two-dimensional Wigner crystals. Then I'll show you some data where we've imaged bare two-dimensional Wigner crystals. And then last, I'll show you some results where we've imaged defect effects in Wigner crystals. And I'll tell you how we've learned a little bit new stuff from quantum Monte Carlo theory. Okay, so what is a Wigner crystal? A Wigner crystal is a crystal of electrons. And I'll just start by just saying that most materials are not Wigner crystals. And the reason is because for most materials, the kinetic energy of the electrons dominates. It's the dominant energy of the system. And that makes the electrons move around. And they swim around like water, like waves in the ocean. And they behave like a liquid. In fact, that's what we call them, a Fermi liquid. And you can see that, for example, in STM images. This is an STM image of copper. And you can see how the electrons behave like water, like little waves. They're behaving like a liquid, a Fermi liquid. However, if you're able to, if you work hard and reduce the density of the electrons and reduce the screening, then you can engineer your two-dimensional system such that the potential energy of the electrons dominates. And when I say potential energy, what I mean is the Coulomb repulsion between electrons. If that Coulomb repulsion is so strong, then the electrons don't have enough energy to move around, so they stabilize into a lattice, a triangular lattice that we call a Wigner crystal. And we call it that because Wigner was the first person to predict this back in 1934. And so you can think of it as analogous to how water freezes. We know how water freezes. We have solid phase, we have liquid phase, we have mixed phases. However, water molecules are charge neutral. They behave mostly classically, whereas electrons, at least the electrons I'll be talking about, are in a quantum regime and they're charged. And so when electrons do this, they do it a little differently. Nevertheless, when the electrons are deep into the Wigner crystal phase or deep into the Fermi liquid phase, then we kind of understand them reasonably well. But it's really when we start to go to the boundaries of the phases. For example, when we start to freeze the Fermi liquid, or when we start to melt the Wigner crystal, then we have some interesting. Things become a little harder to understand. When we start having these predictions that have not been seen yet, for example, people have predicted that there should exist intermediate microemulsion phases that exhibit complex geometries of mixed phases of solid and liquid electrons and stripes and bubble phases, even in the absence of a magnetic field. And these have never been seen. There's also other predictions of magnetism. There should be changes in magnetism across this whole phase diagram, from ferromagnetic to anti-ferromagnetic. There's plenty of predictions that have not been that people have not tested yet. Also, there's open questions about what happens when you have defects in these systems. How do the defects affect all of this physics? So there's a lot of things that are unknown about this kind of physics. But if you want to understand it, then the place to begin is here. This is the most important quantity for understanding this kind of physics. It's the ratio of the potential energy to the kinetic energy of a system of electrons. And in solid state physics, we have a name for this. We call it RS. And weirdly enough, this is equal to the distance between electrons in units of the Bohr radius. I think that's not completely obvious, but it's pretty easy to show. So we call this ratio RS. And what that means then is if that ratio is not very big, that means your potential energy is small. And that means that the electrons are close together, in which case you expect them to behave like a liquid. On the other hand, if this ratio is big, that means that the potential energy is strong and the electrons are far apart, and then they're more likely to behave like a Wigner crystal. So it's worth it for us to take a closer look at this ratio. So let's do that. So potential energy per electron is pretty easy to understand. It's just the familiar Coulomb repulsion formula that we all know and love. The kinetic energy is a little harder. In the two-dimensional quantum limit, which is a limit that I'm going to be talking about today, the kinetic energy per electron can be written in this form. And basically what you do is you just add up all the quantum kinetic energy from the bottom of the band up to the Fermi energy, and that's how you get this expression. I want to mention that for a classical Wigner crystal, this kinetic energy per electron would be kT. But we're in the quantum regime. But I do want to mention that for most atom trapping experiments, this is kT, not rather than this expression. Okay, so if we just can take the ratio of those two expressions I just showed you, then we see that this ratio, this RS factor, is proportional to the mass of electron divided by the square root of the density of electrons times the dielectric constant. And so this is a really useful thing to notice, because it's telling us that if we want to make a Wigner crystal, we want that ratio to be big, and that means we want the mass of the electrons to be big, low density, and low screening. So that's really easy to show. I just showed it. However, what's not so easy to show is to know what is the precise dividing line, the precise value of this ratio that divides the liquid from the solid phase. That's really hard to figure out. But luckily, some smart people in the late 80s, Tanatar and separately, did some quantum Monte Carlo calculations, and they predicted that for two-dimensional electrons, that dividing line is right when this ratio, RS, is equal to 37. The answer is 37. And so what that means is that if this ratio is, they predict that if this ratio is bigger than 37, they predict that the electrons will freeze into a crystal, whereas if this ratio is smaller than 37, then the electrons should be in a liquid phase, according to their prediction. So since I'm an experimentalist, my job then is to figure out how to make this ratio really big so that we can see this Wigner crystallization phenomena. And we're not the only ones to do it. Lots of experimentalists for many decades have been studying this. And if you look at all of the work that's been done for the last 50, 40 years, however long, then you'll notice that it really can be divided into three different regimes, three different techniques that experimentalists have used to make this ratio big. The first, I like to call them the B-field technique, the superlattice technique, and the bare high mass technique. So what I'm going to do right now in this talk is I'm going to go through each of these in that order. So let's start with the first one, B-field. Wigner crystal strategy number 1, crank B-field up really high. The reason why this is a good thing to do is because it makes the electrons go in circles. And when electrons go in circles, they form Landau levels. And you can think of Landau levels as flat bands that have high effective mass. And that quenches out the kinetic energy. And it makes this ratio big, which is good if you want to see a Wigner crystal. So people have known this for many decades. And even back in the 80s and the 90s, people were doing this. For example, back in the 80s and 90s, solid-state physics' favorite two-dimensional platform back then was this heterostructure where you take gallium arsenide and you put it on top of aluminum gallium arsenide. And then what people did was they stuck electrons at the interface, and so they were trapped two-dimensional electrons, and then people would measure the resistance of those electrons, and they saw evidence, lots of evidence for Wigner crystallization. So they saw it, a long time ago. And more recently, Ali Yazdani's group at Princeton has used this trick to see Wigner crystals in graphene. They took a bilayer of graphene, they stuck it in a magnetic field at 14 Tesla, and they were able to see a Wigner crystal at high field, as you see here. Okay, well, that's all I want to talk about Wigner crystal strategy number 1. Now let's go to Wigner crystal strategy number 2. See, this is going to be a really fast talk. So Wigner crystal strategy number 2 is to put the electrons into a superlattice. And in solid-state physics these days, our favorite superlattice is the moire materials. And the way it works is you take 2 single-layer materials, like I show here, and you put one on top of the other. Now, if the 2 materials have a difference in lattice constant, or if you put a little twist between them, then you get an interference pattern like what you're seeing up there, and that defines a new periodicity, the Moiré periodicity, and that's a superlattice. Now, for some materials, that superlattice behaves a lot like the Hubbard model. The materials, for example, are the transition metal dicalcogonide materials that I list right here. So let me tell you what a Hubbard model is. Now, Greiner actually gave a talk here a few weeks ago. He gave a great talk where he talked a lot about the Hubbard model. But I'll remind those of you who didn't go to that talk. So the Hubbard model is when you stick some electrons into a superlattice, then those electrons, which are the red balls in this picture, they can hop around. And they have an amplitude to hop, a T. You can think of that as T for tunneling, because they tunnel from one side to the other, and they can hop around like that. They hop around until they encounter another electron, and then when they hop into that place where there's another electron, then they have to pay a high energy for double occupancy. That's a Coulomb energy for double occupancy. So the two parameters for the Hubbard model are T and U, and solid state physicists love this model because it's so simple. That's it. That's the whole model. But it's really leads to a lot of complex physics. So that's kind of cool. It was this model was this Hubbard made this model back in 1963, but shortly after this model was invented, people realized, including Hubbard, that there's a lot of phenomena in solid state physics that requires more parameters than what you see in this model. For example, for a lot of the physics that we see in condensed matter, long-range Coulomb interactions also play a role. And so Hubbard, actually in 1978, Hubbard extended the Hubbard model and by adding long-range Coulomb interactions. So that's a Coulomb interaction between electrons in different sites. So that's this term V. And in that paper in 1978, Hubbard predicted that if this long-range Coulomb interaction is really strong, then electrons will crystallize in the Hubbard model. He predicted they will crystallize when the filling factor is equal to a rational fraction, like 1/3, as I draw up here. And so here's the filling factor. Nu is the filling factor. It means number of electrons per unit cell. So here the filling factor is 1/3. That means I have 1 electron for every 3 unit cells. You can see the little red balls, they've frozen into a crystal. And I think that this is kind of intuitive because you can see that that crystal is just minimizing Coulomb energy, which is what the electrons want to do. And so this is a crystal. It's an electron crystal. It's a Wigner crystal because it's stabilized by long-range Coulomb interactions. But because it's getting a little bit of help from this superlattice, we call it a generalized Wigner crystal. And it turns out that recently a lot of different groups have seen exactly this kind of behavior, but in two-dimensional Hubbard models, in two-dimensional superlattices in the transition metal dichalcogonide materials. Here I list some of those groups. And they use optics, microwaves, and transport to observe this kind of physics. And they saw evidence for generalized Wigner crystallization for example, these types of filling factors. So this is nu equals 1/3 so this is a triangular lattice. And so the generalized Wigner crystal at nu equals 1/3 on a triangular lattice, you expect this. The red dots are the electrons, the open circles are the empty sites, and this is the pattern that minimizes Coulomb repulsion. For nu equals 1/2, 1 electron for every 2 unit cells, you expect stripes. For nu equals 2/3, you expect a honeycomb pattern. So these are the Wigner crystals you would expect. But and so these folks saw evidence for this, but they actually never quite knew whether or not they really had the two-dimensional crystals. Because they couldn't visualize them. They couldn't see the two-dimensional crystals. And so the first people to actually visualize these two-dimensional crystals was a collaboration between Feng Wang's group and my group back in 2021. And so what we did to image these Wigner crystal states is we took a moiré superlattice and we sandwiched it between boron nitride, as you see in this little cartoon, and then we put it on top of a silicon wafer, and we put a piece of graphene on top, and we charged up those electrodes, and so that allowed us to put electrons into the moiré the same way that you charge up a capacitor. And so that's called gating. And then what we did was we looked at the top with a scanning tunneling microscope, and the idea is to visualize what these electrons are doing by seeing how they disturb the electrons in the graphene on top. And so that's what we did, and surprisingly, it worked. And so this is a more detailed sketch of the device, and you can see that what we did was to put 1 layer of tungsten disulfide on top of a single layer of tungsten diselenide. And the people who actually did the work was Hongyun Lee and Xiaowei Li. They did the heavy lifting. They took the data. And so what they did was they imaged this top layer of graphene, the sensing layer, with the STM. And what an STM is, is a sharp metal needle attached to a piezoelectric crystal. That piezoelectric crystal moves it around, and electrons tunnel from the tip in the sample. You measure that tunnel current, and it allows you to image very, very small objects. And so they use this technique to image that, and let me show you what they saw. Here is what they saw for nu equals 1. That's a filling factor of 1 electron for every moire unit cell. And so now the moire is completely filled. So there's a single electron sitting on every moire unit cell. And you can see that here in the image. That's the image of the graphene on top. So that is not a Wigner crystal. That is not a generalized Wigner crystal. That is actually a Mott insulator. To see the Wigner crystal, what we have to do is remove some of those electrons. So now let's reduce the filling factor down to 1/3. So now I only have 1 electron for every 3 moire unit cells. And now you can see, we see this bigger triangular pattern, which represents this pattern of electrons. And so this is a Wigner crystal. This is a generalized Wigner crystal. It's a 2-dimensional crystal of electrons that's stabilized by the long-range Coulomb interactions. And it's on the same patch of surface. So then we just have to tune the knob on the power supply to put a different number of electrons in there. And then the electrons rearrange themselves into a stripe pattern. This is nu equals 1/2. 1 electron for every 2 moire unit cells. And you can see the stripes. And for nu equals 2/3, you can see the honeycomb pattern. So these are the patterns that are predicted to minimize Coulomb repulsion on a triangular lattice. But I want you to notice that the spatial resolution is not so great because the electrons are buried. They're underneath. So that's what we did a while ago. And so lately now it's 5 years later. And so we're actually still interested in this physics. We're still interested in these generalized Wigner crystals. But lately we've been interested in how they melt. And so we've been studying their melting properties. So here I show a nu equals 2/3 honeycomb Wigner crystal. And so now the question we're interested in is what happens, for example, if we add electrons to that Wigner crystal, which we call electron doping? Or, on the other hand, what happens if we remove electrons, which we call hole doping? The question is, what happens? And so that's a question that we're interested in. We want to know what happens. Theorists have made a bunch of predictions about this. So lots of theorists have gone to town on this problem. And let me mention some of the predictions that the theorists have made. For example, some theorists believe that when you add electrons to that generalized Wigner crystal, the electrons, the prediction is that you'll only get partial melting. The prediction is that the Wigner crystal, which is represented by the balls, will just sit there stationary, whereas the electrons that you add will run around and form a little liquid moving around those pins. And they call this a pinball liquid. That's what they actually call it. It's a technical term. And so this little Gaussians, those are meant to represent sort of the metallic electrons running around the frozen electrons. So that's one prediction. Another prediction is that when you add those electrons, the prediction is that the Wigner crystal will just melt. It'll just turn into a liquid. All the electrons will just melt and form a delocalized Fermi liquid. So that's another prediction. And yet another prediction is that when you add the electrons, the Wigner crystal won't completely fall apart, but it will become disordered, and you'll get little crystallites here and there, like a slushy. And in fact, they call it electron slush. That's the technical term. And so there's lots of predictions of this type. And so we decided to test these predictions. And so the way we did it was we had to build a device that had higher spatial resolution because we wanted to see things a little bit better. And so to do that, we took 2 layers of one layer of MOSE2 and another layer of MOSE2, and we put one on top of the other, and we gave it a twist. And then we incorporated it into a device that looked like this. And so now you can see that this moire is stuck on top of boron nitride, on top of a silicon wafer, and we put a piece of graphene on top. But as you can see, we cut holes into the graphene so that we can do STM in the little holes. This device was made by Emma Berger and Michael Arumanayagam. They did the heavy lifting on this project, and what they saw when they did STM here was the moire pattern. So that's the STM image. That's the moire pattern here that I represented in the cartoon. That's the reality. It's a triangular lattice. If we zoom in, you can see the triangular lattice. But to see an electron crystal in that triangular lattice, we have to add electrons. And the way we do that is to put a positive voltage on this back gate, and we charge it up like a capacitor. It is a capacitor. And it's represented by this little diagram. This is energy versus vertical distance. The electrons that are sitting in that moire go into the conduction band. That's represented by the red color. We put a positive voltage on the tip that pulls it down in energy, and these electrons can then tunnel into the tip. and we measure the tunnel current. And that tunnel current is proportional to the local electron density. That's how we take a picture of the local electron density. And so this is what the pictures look like. First, I just want to mention that the two crystals that we were most interested in was the stripe crystal, nu equals 1/2, and the honeycomb crystal, nu equals 2/3. So when we took pictures of those, they look like this. So here I'm showing you an STM image of the nu equals 1/2 striped electron crystal. Notice that now the spatial resolution is much better because we're using this open phase geometry instead of the sensing layer geometry. Each bright dot there is a single electron. Here's the nu equals 2/3 honeycomb electron crystal. And so what we're interested in is how these crystals melt as we add or subtract electrons so that we can test those predictions. We actually saw very similar behavior for both types, striped and honeycomb. I'm only going to show you the data for the honeycomb. And so I'm going to show you how it melts. But before showing it to you, I just want to mention that when we did this, we saw something unexpected. What we discovered is that the crystal melts very differently depending on whether we add electrons or remove electrons. So in our language, we say electron doping versus hole doping. And the fact that it's different in those two ways, we call that electron-hole asymmetry. And so we saw an unexpected electron-hole asymmetry. So now I'm going to add electrons to this. I'll show you the data. First, this red color is the filled electrons. So right now it's filled up to nu equals 2/3. Nu equals 1 would be total filling is up here. So that part is empty. So I'm going to make that arrow go up. I'm going to add electrons. So let's add some electrons. Now you can see that it's melting here in the lower left. Let's add some more electrons and some more. You can see it's melting. There's a front, a melting front. Let's melt. I'm melting, it's melting. So now it's totally melted. So now it looks as though there's an electron at every site. It looks like it's all filled up with electrons, but it's not. See? There's not enough electrons to cover this lattice. And so what we believe is happening is that we're getting Fermi liquid behavior. We believe that the crystal has completely melted and that now the electrons are delocalized like a liquid. That's what we believe we're seeing, this uniform melting. Now let's see what happens when we remove electrons from the crystal. So let's go back to nu equals 2/3. And now let's start removing electrons just by putting a negative gate voltage on the bottom gate. And so now this little arrow is going to go down. So let's remove some electrons. Now let's remove some more. Now let's remove some more, and some more, and some more. Notice there's no uniform melting. It just gets this, you just see this weird disorder. Let's do some more. Let's remove some more and some more. No uniform melting, only this weird electronic disorder. And so what we think we're seeing here is the electron slush that was predicted by theorists, because what we're seeing is just this completely disordered crystallites. We're seeing little crystallites of the electron crystal. It's not completely melting, but it's just becoming completely disordered. Now, to us, this is really interesting. And the reason why it's interesting to us is because this disorder is coming about not because of disorder in the structural disorder, but it's coming about, it's emerging from the electron-electron interaction. So we believe it's an electron-driven disorder due to the interaction because of frustration. It's a competition between different order parameters. Okay, so now let's go back to these predictions. So we did not see evidence for the pinball liquid, but we did see evidence for the Fermi liquid when we did electron doping. We did see evidence for the electron slush when we did hole doping. So that's all very nice. But the question in our minds is, why did we see this asymmetry? Why did we get uniform melting for the electrons? Why did we get disordered electron slush for the holes? That really confused us. We had no idea why that was. But then we got some help from Michael Zalatel's group. Michael Zalatel and his postdoc, Ji-Wan Dong, they did some calculations, Hartree-Fock calculations, and their calculations suggest that the reason why we get uniform melting for adding electrons is because when you add electrons, they have to come in at very high momentum. And so when you look at the wave function of the high momentum electrons, the nodal pattern and the antinodes interact very strongly with the Wigner crystal, and you get very strong Coulomb repulsion, which causes the Wigner crystal to just fall apart. On the other hand, if you remove electrons and you're adding holes, the holes come in with very low momentum, and so their wave functions are very featureless, and so they don't interact so strongly with this generalized Wigner crystal. And that's why you just remove some electrons, you get disorder, but not a complete melting. And if you want to know more about this, you can look at this paper that we recently posted on the archive. Okay, well now I want to go to Wigner crystal strategy number 3, the third and final strategy, which is bare high mass Wigner crystals. And so now I want to tell you about bare Wigner crystals. And when I say use that term bare Wigner crystals, what I mean is in the absence of a B field and in the absence of a moire. So let's take the training wheels off. And so there's really no trick to make a bare Wigner crystal. Really, there's just this ratio, this RS ratio. You just want to make it big. And so the only thing you really can do is increase that mass or decrease that density and get rid of screening. And so that's what we got to do. But I just want to say other people thought of this before us. Other people have done this a long time ago, and they've also other people have seen evidence for bare Wigner crystals. And so even in the 90s, people were doing this. So I will mention one experiment, which is an experiment done by Shayagan's group in 1999. And what they did was they took a gallium arsenide on top of aluminum gallium arsenide. So they have this interface, and instead of adding electrons to the interface, they added holes. The reason they did that is because the mass of the holes is bigger and it makes that ratio bigger. And so it helps to create Wigner crystals. And they actually saw evidence for Wigner crystallization. Here I'm showing their data. What they measured was the resistance through this interface as a function of temperature, resistance versus temperature. And what they saw was a metal insulator transition as they reduce the density. Here at the bottom is high density. The resistance versus temperature goes down. That's metallic behavior. At low density, the resistance versus temperature goes up. That's insulating behavior. And so this metal to insulator transition is evidence for Wigner crystal because you expect Wigner crystals to be insulating. So this is quite nice data, but I don't want to rain on anybody's parade, but still there's some problems, you have to worry about when you do measurements like this. You got to worry about defects when you do this, because when you do a transport measurement, defects can actually cause metal insulator transitions due to physics that has nothing to do with electron-electron interactions and has nothing to do with Wigner crystallization. For example, Anderson localization can cause a metal insulator transition. Anderson localization occurs when electrons scatter off of defects and it causes localization of the wave function and insulating behavior, even in the absence of electron-electron interactions. And so look at that picture and now compare that to the Wigner crystal. And you can see how different it is just from my little PowerPoint drawing. The wave function looks very different. So these are very different physics, but if all you do is measure resistance, it's hard to know which one you're seeing. And so for us, this motivates us, because what we want to do is we want to do this. We want to study the same kind of physics, but we want to use a technique where we can simultaneously image the electrons and the defects, because we feel that that will then help us to figure out what's going on. It'll give us useful additional information. So that's what we did. And the way we did it was to take single layers of TMD material. We made devices out of them without any moire, without any B field, and we added electrons and holes, and we looked at it with our STM. Because that's what we do. And so then one of the first materials that we looked at is this, bilayer MOSE2. And what bilayer MOSE2 is, it's 2 layers of MOSE2, but naturally stacked. No twist. There's no difference in lattice constant. So we really think of it as just one layer of material, but just with 2 layers in it. So that's what it is. And so the reason why we chose this is because when you look at the band structure, and by the way, this band structure was calculated by Stephen Louie's group, with Mitnaik, the band structure gives us the energy versus momentum for all the electronic eigenstates inside of that crystal. And when you look at that, you can see from these little parabolic regions here that you can get the mass of the electrons and the mass of the holes. And when you look at this band structure, what you learn from it is that the effective mass of the electrons and holes is pretty big by our standards. And that's good because that helps us to make a Wigner crystal. And so if you take this prediction for when the Wigner crystal occurs, where this RS value of 37, you can work backwards pretty easily, and you can show that the critical density for electrons in this material is 4 times 10 to the 11 electrons per square centimeter, whereas the critical density for holes is 3 times 10 to the 12 holes per square centimeter. And what that means is that if you put more charge carriers than that, then you expect the charge carriers to liquefy and be a liquid. If you put less, then this prediction is that those electrons will crystallize. And so furthermore, I just want to add that Other groups have seen evidence for Wigner crystallization in single-layer TMD materials using optical techniques. They shine light on it. They cannot visualize the Wigner crystal, but they do have very compelling indirect evidence for Wigner crystallization, which is good because that gives us more hope that we will actually be able to see it. So in order to visualize the Wigner crystal in this material, what we did was to make this device. This device was made by Siyu Zhang, Hongyun Lee, and Zhonghan Shao. They did the heavy lifting for this sub-project. And what they did was to take a bilayer of MOSE2, they put it on top of boron nitride, on top of a graphite backgate, on top of boron nitride, on top of a silicon backgate, and they put a piece of graphene on top. And they cut holes in the graphene so we could do STM in the little holes. And the first thing they did, well, maybe it wasn't the first thing, but one of the things they did was to put a negative gate voltage on the back to dope holes into this bilayer MOSE2 material. And what they saw when they did that was this. What you're seeing here is every little bump that you see in this image is a single charge carrier, a single hole. Now, the holes, as you can see, are localized because they repel each other. They're positively charged. They repel each other. This is a Wigner solid. I don't call it a Wigner crystal because it lacks long-range periodicity, but it's a Wigner solid. And so what we can do now is we can add more holes to it and see what happens. And that's what we did. So here I have 2.6 times 10 to the 12 holes, 4 times 10 to the 12, 5, 6, 7 times 10 to the 12 holes per square centimeter. And what we see is that as we increase the density, the holes get closer together, as you would expect. But what we also see, which is non-trivial, is that when you increase the density, we get certain regions where the corrugation appears to become reduced, to become flatter, like right there. See, you get these flat regions. And what we believe is happening is that the charge carriers are melting in those regions. What we believe we're seeing here is the coexistence of liquid and solid charge carriers. So let's take a closer look at this. Here's a nicer image at 5.3 times 10 to the 12 holes per square centimeter. Now let's go up. 5.7, 6.1, 7.0. And what you can see is that as we increase, what I've done is I've circled the regions that we believe are melted. And you can see that as I increase the density, those regions get bigger. There's more melting. And that makes sense because as you increase the density of charge carriers, you're increasing the kinetic energy. You're making it more likely to melt. So this makes sense. But the part of it that was confusing and did not make sense was the fact that this solid liquid phase coexistence occurred over such a wide range of density, all the way up to 7 times 10 to the 12. The reason that's weird is because remember the prediction of the critical density of holes was 3 times 10 to the 12. So now way up at 7 times 10 to the 12, we're still seeing lots of evidence for a solid phase. And that was weird. And so what we think is happening, what's causing this is the presence of defects in the system. So we believe that defects are causing this. And so this motivated us to take a closer look at the defects. But that was kind of hard to do because this first generation of devices had some contamination on the surface, and it was really hard to get atomic resolution to see the defects. So we had to do a lot of work to clean up our devices. And that hard work was done by Jiehao Gei, Seihao He, Shiza Li, and Betty Hu. What they did was to develop a new device fabrication protocol that allowed us to have much cleaner devices. And they made this kind of a device, which is very similar to the one I showed you before, but was a lot cleaner. And they took the bilayer MOSE2, they put it on top of boron nitride, on top of a silicon wafer. We have graphene on top. We cut holes in the graphene, and we can look at it with the STM in the little holes. And what we see is this. Now we can get really good atomic resolution. We can see the defects in our devices quite nicely. We can see these ones, these big scary ones are charge defects. These cute little ones are neutral defects. We call them isovalent defects. They're charge neutral. And we can actually identify some of those defects by comparing our images to images that other people have published in the past, such as Alex Weber-Bargioni and Bruno Schuler and other folks. And so we know that some of these defects are impurities, some are vacancies, some we have no idea what they are. And we got different densities of defects in our devices depending on what crystal we used. And we actually saw very different behavior depending on the density of defects, qualitatively different behavior. But what I'm going to do now is I'm going to show you some data that we saw for the low end of the defect density, what we call, for us, low defect devices, which is when the defects are here at around 10 to the 11 defects per square centimeter. So Here I show an STM image of one of our low defect density devices. There's no electrons here. It's just an STM image. What I've done is I've circled all the charge defects with little red circles. I want you to remember. I want you to memorize where those little red circles are. I know that's impossible, but try anyways. So you can also see the charge neutral defects in the background. I did not circle them because they don't play such a big role, such an important role in the physics I'm about to show you. So now let's add some electrons to this device and see what it looks like. So let's add 2.7 times 10 to the 11 electrons per square centimeter, and this is what you see. You see the electrons. This bright blob is 1 electron. That's 1 electron. There are 16 electrons in this image. You can see that the electrons are highly localized. They're pushing against each other because of Coulomb repulsion. They're also pushing against these charge defects. They're trying to form a triangular lattice, but they are frustrated by the defects. So I would call this a Wigner solid. It's a crystal. It's a solid of electrons trying to be a crystal. Now let's add more electrons. Let's increase the density to 3 times 10 to the 11. And now you see some destabilization of the electron solid. We call this local melting. So now let's add more electrons. And what we see is more electrons. But we also see the local melting. Now let's add more electrons. And now we see something interesting. What we see is a stabilization of the electron crystal. Now we see it looks like for us, we consider that to be a pretty good Wigner crystal. You can see that the electrons are really, trying to form a triangular lattice. They're nicely crystallized. We call this reentrant crystallization, and we saw a lot of this. We would add electrons, and they would melt, and then they'd recrystallize, and they'd melt and recrystallize. So here, let's add some more electrons, and now suddenly they get all melty. Now let's add more electrons, and now they become much more crystalline. And so now melted, now more crystalline. And you can see that we start getting these little pearl necklaces around our charge defects. The electrons start to circle the charge defects like a little Christmas wreath. And so let's add more electrons. Now it looks very melted. The electrons are very liquid-like here, and we still see this wreath around the charge defect. Now let's add more electrons and more and more. And this is the highest density, 2.3 times 10 to the 12 electrons per square centimeter. Now you can see that the electrons are completely melted. So we believe that this is a Fermi liquid. And these little rings around the defects, in solid-state physics, we call those Friedel oscillations. And they're sort of like standing wave patterns at the site of the defects. So this is very liquidy behavior. And so what you've just witnessed is the full evolution of the two-dimensional electron gas from the Wigner crystal to the Fermi liquid phase without a B field or a moire. No one's ever seen this before. And it's not published. So you guys, not many people have seen this. Okay, so what does it mean? What do we learn from it? Well, good question. That question's hard. It's hard to answer because, as experimentalists, what we like to do is we like to take our data and we like to compare it to a theory, and it'll either agree with the theory or disagree, and that's how we learn stuff. That's how we learn things. But the problem that we have is that there's no theories for these images. There is no theories out there. And the reason for that is because this Hamiltonian is very hard to diagonalize. That's the Hamiltonian that governs the behavior of those electrons that I just showed you. You can see I have kinetic energy, I have the electron-electron interaction, I got the electron impurity interaction. And it turns out that the regime in which we're doing our experiment puts this Hamiltonian in a very difficult regime to solve for this. So the theorists have a lot of difficulty with this Hamiltonian because these electron-electron interactions are so strong. And what that means is that our favorite theories, density functional theory, Hartree-Fock theory, they rely on the mean field approximation, and so they don't work so well when we have really strong interactions. And so we decided to try there are many theories to try from, but we decided to try quantum Monte Carlo theory. And so let's talk about quantum Monte Carlo for a minute. Dance break. Okay, so quantum Monte Carlo. There's the quantum Monte Carlo wave function. I bet most of you have never seen it before. There it is, in all its glory, and part of it looks familiar. That part right there, that's a Slater determinant, and the Slater determinant is everybody's favorite many-body wave function. That's the many-body wave function that we teach the students in Physics 137b. And for example, if you have 100 electrons, then this is a 100 by 100 matrix. The orbitals are on the row, and the different electrons are in the column. and it gives you anti-symmetrization. So this is everybody's favorite many-body wave function. But the problem with the Slater determinant is that there's no electron-electron interactions in the Slater determinant. And so there's no correlations in that wave function due to electron-electron interactions. And so to get those correlations, those electron-electron interactions, what the quantum Monte Carlo guys do is they add this little part here called the Jastrow factor. And so then what they do is they use a very clever stochastic process to optimize this wave function. It's a variational procedure because they want to minimize the expectation value of the Hamiltonian, that Hamiltonian. And so by doing this optimization process, they can get a very accurate many-body wave function solving this Hamiltonian. So it works pretty good. And it does not rely on the mean field approximation at all. But the problem with quantum Monte Carlo is that it's only good for about 100 electrons. If you have more than 100 electrons, then the computer's not big enough to solve it, and there's no computers big enough to solve it. So that's the problem, because often in solid-state physics, often we have more than 100 electrons. Often we often have Avogadro's number of electrons. So we still need density functional theory and Hartree-Fock. But for us, this actually worked pretty good. So let me show you. So what we did was we used quantum Monte Carlo to solve this Hamiltonian. We compared it to our data. But when I say we, I mean royal we. I mean, I didn't do it, but these guys did it because I don't know how to do quantum Monte Carlo, but these guys do. Shiwei Zhang is a theorist at the Flatiron Institute, and he has a whole team of theorists, and they're all experts at quantum Monte Carlo. So we collaborated with them, and what we did as experimentalists, we gave them the density of electrons, we gave them the mass of the electrons, we told them the size of our pictures that we took on our STM, because these are things that we know. We told them where the defects are, and what they did was they constructed in their computer, they constructed an energy landscape in their computer by taking Coulomb potentials and putting them at the precise locations of our defects. So they constructed this energy landscape in their computer, and then they populated that energy landscape with electrons, and then they found the ground state. They used quantum Monte Carlo to find the ground state, and then we compared that to our experiment. And there's no fitting parameters here except for one, which is the dielectric constant. The background dielectric constant was the only fitting parameter here. Okay, so now let me show you the results of their calculation. So this is the energy landscape that they constructed in their computer. And notice these little red circles, that's where the charge defects are. That's why I asked you to remember the locations of the charge defect. Notice it's the same pattern. So they put a fixed negative charge at each location of the circle, a fixed Coulomb potential. Then they populated this landscape with electrons. And here, the first one they did was 2.7 times 10 to the 11 electrons per square centimeter, which is the same amount that we did experimentally. And this is what they saw. So this is the result of their calculation. So what you're seeing is the wave function, the ground state, psi star psi. So this blob is a single electron. That blob is a single electron. These are all electrons. You can see how the electrons are localized. They're pushing against each other because of Coulomb repulsion. They're pushing against these negative charges here. They're trying to form a triangular lattice, but they're frustrated by these defects. And I just want to say that this actually looks a lot like what we measured experimentally. So now let me show you what they saw when they added more electrons. So now let's add more electrons, but this is all quantum Monte Carlo. This is all theory. They see local melting, just like we saw experimentally. They see the same phenomena. It's not exactly the same, but it's pretty similar. Let's add more electrons. You see more electrons. Now let's add more electrons. Now let's add more electrons. Now you can see that it crystallizes. The local melting is mostly gone, and now the electrons are more crystalline. So this whole reentrant crystallization phenomena, they also saw into quantum Monte Carlo. Now let's add more electrons. And so this is all the results of their theory, the quantum Monte Carlo. And it looks a lot like what we saw experimentally. Here you can see the pearl necklace is starting to form around the defects. The electrons are, this is what comes, the precursor to a Friedel oscillation. Now let's add more electrons and more and more. And let's go to the highest density of electrons. And so here is the highest density that they could handle experimentally, 7 times 10 to the 11 electrons per square centimeter. And you can see that they have a liquefied region here, and they have a solid region here. The electrons are starting to circle the charge defects. Unfortunately, this is the highest that they could go, 7 times 10 to the 11 electrons per square centimeter, because that's about 100 electrons. They can't do more. Their computers are not big enough. Nobody's computer is big enough, unfortunately. We need bigger computers. Uh, but nevertheless, it's pretty good. You know, they see this looks a lot like what we saw experimentally. And so here I show a one-to-one comparison of the theory and the experiment. The experiment is here on top. The theory is here on bottom for 3 different electron densities. And they look pretty similar. And so this is the first time that anyone's ever compared quantum Monte Carlo to STM. And I think it works pretty good. And so, for example, they also see increased critical density, similar to what we saw. They also see the reentrant crystallization phenomena that we saw. And we actually learned something new from all of this, from all this work. We actually learned something new. The new thing that we learned is that the isovalent defects are not important in this physical regime. And the reason how we learned that is because the theorists did not include isovalent defects in their calculations, and yet they still matched our experiment quite nicely. And so this is telling us that for this physical regime, isovalent defects don't play a big role. And that's actually genuinely useful information. Unfortunately, they could not go to the highest densities that we went to. For example, we went all the way up here to 2 times 10 to the 12th. We got full liquefaction. So they could not calculate that for this scan size because it's just too many electrons for them. However, you know, theorists, they're so clever. They came up with this clever workaround. So they decided to just simulate just a small piece of our image, and they used periodic boundary conditions. You know, so they just created their own little world right there. And then they added electrons and did quantum Monte Carlo, and it worked quite nicely. Adding a lot of electrons, the same density of electrons, they see the same behavior that we see, even in the liquid range. So the point I'm trying to make is that the quantum Monte Carlo really reproduces our experiment from all the way from the Wigner crystal all the way to the liquid phase, and including the Friedel oscillations. Okay, well, I'm almost done. Let's see where I am. Okay. Yeah, okay, so I'm almost done with my story, and I'll just say a few words about the future. For the future, there's a lot of interesting things to do. Here I just list a few of them. For example, we would like to observe the intermediate states that have been predicted but never seen, where people have predicted complex bubbles and stripe phases at zero magnetic field, these mixed phase regimes. We would also like to see if we could observe spin effects. And also, I will just mention this multi-valley business. I did not mention this, but in our materials, the electrons are living in different valleys in reciprocal space, and the electrons in different valleys in principle can interfere with one another. You can get inter-valley coherences, and we actually see evidence for that. Although I didn't show it to you, I don't have time to show it to you, but I think that that could lead to some interesting physics. And the last one here is topology. In solid state physics right now, people are very excited about trying to understand the competition between electron-electron correlations and topology. That's a hot topic in solid state physics. And the theorists have predicted lots of interesting things, such as topological Wigner crystals, where you can get topologically protected boundary states and orbital angular momentum in the Wigner crystal. And so these things would be very interesting to observe. We haven't seen those yet, but we want to. So now I will conclude, and I will conclude by saying that in the past, when we would look at electrons with our STM, the electrons would look like a liquid, like a bowl of water. But now they look like a bowl of marbles. Thanks.
Thank you, Mike. So now open for questions. Yes.
Mike, that's pretty incredible stuff. I have a question again about how this STM imaging works. So you're, of course, with your STM, you're sort of adding, subtracting electrons from this liquid that is made up of single electrons. So why does the injection of current not affect the crystal in a major way or represent the defect in the crystal itself?
Well, okay, so there's two things. First, what you didn't mention, but also you probably were thinking of, is the electric field of the tip. You know, it's a big hunk of metal, and there's also work function mismatch and electric fields. That's what we were mostly afraid of, were those electric fields, and they are a problem. But it turns out that we can tune the electric field. So because there's an energy gap, we can move the tip Fermi level within that energy gap, and that gives us some leeway. So so that for so we're able to cancel that electric field due to the work function difference. But then there's the issue that you just raised, which is what happens when you actually pull the electron out. And so, yeah, that's a good question. Any other questions? So, I mean, I don't know. I don't have a good answer to your question. I mean, there's electrons here. We pull one out, it goes into the tip. Then we wait a while, and then another electron has to come and replace it, and then it has to sort of come back, right? And then after a while, another electron jumps in. Then we wait, it gets back to where it was, and then another one jumps in. And so that's sort of my picture, for the process. And so the question then is, and there's time, between the electrons, because it's a single electron process. The tunneling is like one electron, then another. And so, but the question then is, how does the system, come back? And so another electron has to come back and replace that one. So clearly, I think it's working. It's happening, because like the images look so close to the quantum Monte Carlo. It gives me some confidence that we actually are seeing, this kind of physics. And so I think that the time between electrons jumping is enough time for another electron to replace the one that we yanked out. But how that replacement actually occurs is very confusing to me.
Yes.
Yeah, thanks for the great talk. I had a question about your generalized Wigner crystal melting. Is your setup able to tune other parameters while keeping the electron density fixed? So that you drive an insulator to metal transition
Through the D field. You mean like D field? Is that what you're saying?
Yeah, exactly.
Yeah. Okay, so we have a big problem with that because we only have the one electrode on the bottom. If we want to sort of, that first device geometry I showed you, the sensing layer geometry, we have the top and bottom electrodes. And so in principle there, we can control the D field and the density independently. But the problem then is that, the tip is so far away, we can't do good imaging. And so then where we can do the open phase geometry, we only have the one gate. And so as we change that gate, we're tuning the electron density, but we're simultaneously tuning the D field. And so if you look at the phase space of D versus density, D field versus density, we're just moving on one line across that. Okay, so we can change the D, but not independent of the N. That's a big problem for us, and we would like to try to overcome that, but that's tricky.
Okay, Mike, I wanted to ask a question. It seemed that a lot of, in your last experiment, you described the defects were playing a very major role. So what are the prospects for getting rid of the defects?
Yeah, that's a good question. So, that's really in the realm of the crystal grower. And so there are a number of crystal growers around the world, and they're working very hard to try to remove those defects. And so there, there's all these zone melting techniques, all this very complicated. Where's James Analyzes? Probably isn't here. He's a crystal grower. He knows all about it. Go ask James. But yeah, I don't know. I'm not a crystal grower, but yeah, there is possibility of getting cleaner crystals, and so that's what I'm hoping for. And so that's one of the things we do is we poke around and try to get cleaner crystals.
Okay, yeah.
Yeah, well, when we gate it and go into the whole regime, then we then can see positive defects. But it's sort of like for the electrons, we tend to see only either charge neutral or negative defects, and for the holes, we tend to see only neutral or positive defects.
Yes.
Okay. Okay, you're asking me. Okay, so you're asking why did this reentrant phenomena occur? Okay, so what we believe, and we actually have some evidence to back this up, what we believe is happening is it's the defects. You have a fixed distance between the defects. And so as we add electrons, there's sort of a preferred distance between the electrons, just 1 over square root of the density. That's the distance they want. And so when that distance, when you have an integer number of those distances between the defects, then they're going to crystallize. And so we actually see that when we take Fourier transforms and we, do some fancy Fourier transform analysis, we sort of see that it's like a commensuration in commensuration, if that makes any sense.
Okay, well, let's thank Mike again.